Hi guys, in this video we're going to go through some exam questions for VCE Algorithmics on abstract data types. For each of these questions, pause the video, try them, and try and make sure you understand why the multiple choice answers are wrong. So here we go. First one, this is a question one, should be quite gentle. We enqueue 6, we enqueue a 3, we dequeue the 6, we enqueue the 2, we dequeue the 3, we're left with 2. Gentle enough, I think. Next one, pause. Correct answer here is Q. It's kind of, you could argue it's stack because it just says each survey response will be stored in the order it's submitted. But we've got to read between the lines a bit. Kind of means, or it suggests that we are going to access them in the order they were submitted to. This one is a bit more involved, so we're going to talk through each operation. So when we set the array, we're setting an integer. I often haven't seen it called set, but whatever. We've got an element with the array and its integer that's placed in the array, which leads to an array, so that's fine. When we look up, we specify the array and the integer, and that gives us an element. So it looks like array is okay. With Q, when we enqueue something, we have an element which we add to the queue, which gives us a queue with that new element, so that's fine. When we dequeue something, we have a queue which removes something from the queue. Note that the operations dequeue and pop just return the new queue. They don't give us the top item from the queue or from the stack like Python does. So queue also seems fine. So it looks like straight away we can probably say that A is our answer. But let's talk through the rest of them. When we add something to the dictionary, when we add an element to the dictionary, it gives us a dictionary, but we also need a key. So it needs to be a key element pair or a key value pair to add to the dictionary. So we can see straight away the dictionary is wrong. We can also see that the remove method is wrong because when we remove an element from a dictionary, it should return the new dictionary, not a Boolean. So that is also wrong. Now let's look at the stack. Hopefully we can find something wrong with that. The push method, when we push an element onto the stack, it gives us the new stack, so that's okay. However, when we pop, and I've mentioned this before, I feel like I'm going to mention this a lot. When we pop something, it does not give you the element, it just gives you the stack with the thing removed. Same with a queue. So our answer was A. Next multiple choice. Make sure you've paused. So let's consider it one by one. The array, well, it's just not ordered alphabetically by key. They are ordered by number. It cannot have an unlimited number of elements. We need to define how many elements the array has at the start. It does not only allow sequential access like a list might, but an array, in fact, well, we're left with D, allows access to each element based purely on the index. The answer is D. Alrighty, now some written questions. I think these describe ADT type questions are very hard to get full marks on. And the questions themselves can be a little bit funny. Like it's sometimes hard to get your head around what the examiner is after. So what can I say? Strap in. The first question is gentle enough, so pause, make sure you try it. We want to relate in these questions the abstract features of the ADT to the real life situation. So we've mentioned the first in, first out aspect of a queue, and we've said that means the aeroplanes that arrive first will get to land first. So we're not saying too much extra, but we are relating real life to theory. The next one, I think, is especially hard. So do spend some time thinking about this, and we're going to talk through a bunch of examples. So consider this first example. Each aeroplane is stored as a dictionary with a fuel as a key read to an integer and so on. This is used as the key for another dictionary with the plane ID as the key, allowing efficient lookup. Now, I always hate this version of dictionaries where people use the same key for every single dictionary. We know that we might as well use an array where we have three values being the integers and the Boolean, because we know that The first one is the fuel, the second one is the schedule, and so on. We don't need to look up fuel explicitly. They're both constant time, but it just saves us the space as well as the hashing time. So that's slightly inefficient. Also, in terms of efficiency of being able to work out which plane needs to land next, this makes it easy to see what the values are for a particular plane, but it doesn't make it easy to work out which plane, for example, has the lowest amount of fuel. So I would say this answer is not fantastic. Let's consider the next one. So I've corrected that first problem with the dictionary versus the array. And we're adding the aeroplane to 3 different priority queues, one for each factor. Now, I think in terms of choosing which plane to land next, this is the most efficient because the 3 factors are going to be weighted differently depending, for example, if you've got 2 planes, one's got 70% fuel left, one's got 80% fuel left, that's not going to make much difference. But if you have 2 planes and one has 10% and one has 20%, that is a much bigger deal. So we need to be able to constantly look up, in my view, which plane should land next, and the priority of the planes is going to change as the fuel runs down. The problem with this is that if we look in the priority queue and we find the plane that has the most urgent fuel situation needs to land first, this ADT combination doesn't actually tell us which plane it is. So we'd need to add to that array, we'd need to add the plane's ID. And the third example, so we've added that plane's ID to the array, and then we've calculated a score, and that is used in a single priority queue. Now, I think this would probably be accepted, although, yeah, as I say, you can argue that that's not fantastic because the score would change. So, I mean, one could argue that you would need to go through the priority queue and keep updating the scores. But they've sort of said in the question, we're not too worried about the real way of deciding, does locality really matter, for example? We're just trying to follow the example they've given us. Okay, and if you have any examples of that, it's a good idea to send them to your teacher to see what marks you would have got in their view and how you could improve, because practicing these written questions is really important. Carrying on, pause, have a crack. This is question 2, so should be fairly gentle. We've got 4 examples of answers here. Let's decide what do we think of each of them. Well, the first one, definitely correct. An array, for the second one, the array stores a fixed number of elements, whereas the elements in the dictionary can vary. That is also definitely true. Number 3 sort of depends on the operating system that you're using. And in pure algorithmics, they don't particularly care what an array holds. So it could hold a mixture of ADTs, or it could hold all strings, for example. It's one of those things they haven't clearly defined in VCE algorithmics, so I kind of stay away from it if possible. So I would not choose number 3 there. And number 4 is kind of true that with a dictionary, we have to do some hashing function to work out whereabouts the location in memory is, whereas with the index, there's probably still some hashing function actually. So even if we consider that the hashing function for a key in a dictionary is going to be slightly slower than that for an index, both are constant time. So in algorithmics, we don't really care that one is a slightly longer constant time. They're both going to be feasible in situations as the number of items gets very large. So first 2 answers there are pretty good. Second 2, risky. Okay, I think B is fairly straightforward, and I think these are like obvious examples that you can just crank out straight away. Remember, we've got to justify the example as well as just state it. So if we just said people arriving at an emergency department, we might get 1 mark. Okay, final question for this video. Have a read through and do try the pseudocode for this. Hopefully you have had a go. You're not just waiting for me to talk through. Okay, here I go talking through. Here was my effort. So And I think I've put a problem in here. See if you can see what it is. It's that thing I've been going on about. Just note the syntax here. We've said while incomplete. That's an acceptable way of saying while the incomplete queue is not empty. So while there are things still incomplete on line 1, number 2, we pop the test from incomplete and we do that test and then we push it to complete. Now that is wrong. When we pop the queue, it just removes it. It doesn't put it somewhere else. So what we had to do was this. We allocate test to peak the incomplete. So, and it's kind of confusing because we've got a real life situation, which it wouldn't make sense to pop a queue and then just throw the test away. But that's kind of what we're imagining. So we do the test and we push it to complete. We've got almost exactly the same thing for while there's still things to be marked. For some reason, I messed up the indentation on line 9. And yeah, I think that's a fairly gentle bit of pseudocode. How many pop operations? Well, each one gets popped once from incomplete and once from complete. So that's 12 for the 6 tests. And generally, that is going to be 2n. That should be quite gentle. And finally, I've set this up. You don't have to, but this time I've written define the algorithm as find best. And we like to think about the initialization, doing, and return phases. So the initialization phase, that we say the maximum score at the beginning is 0. Then line 3, while there are still items on the marked pile, we have a look at the test on the top of the pile, and then we pop it. And we've had to say the current is the score of that test on line 6. And lines 7 to 9 is a fairly standard, or 7 to 11 is fairly standard way of finding the maximum of something. If the thing we've got now is bigger than the maximum, then we set the maximum to the thing we've got now. And in this case, on line 9, I've pushed the test to the incomplete pile. If you look at the VCAR exam report, they put it on the table, but this is also fine. Otherwise, we push the test to the marked pile. So what will happen, we might end up with a few tests in the incomplete pile, and when we peek at the incomplete pile, the most recently added one will be the best one. And so we've got our return phase, which is simply, well, you could say it's 12 and 13, or we could just say it's line 13. We make sure that we return the best test. A mistake here you may have made, you may have returned the best score. So read the question very carefully.